Hi, I'm Graham Markle. I'm a software engineer at NVIDIA, where I've been for about 18 months now, and I spend pretty much all my working time on Numba or related things. I also worked on Numba a bit in the past when I was at Anaconda between 2014 and 2016. So if you get any questions in the future or you want to talk about anything related to Numba and CUDA, then reach out to me anytime. So over the next 30 minutes, I'm planning to spend about 15 minutes talking about Numba and CUDA, then 5 to 10 minutes for a short demo, and whatever time's left over for any Q&A. So what I'm aiming to do is just to give a fairly broad and high-level introduction to Numba and CUDA, nothing too deep, nothing too technical, to help you start to understand what Numba is, who's using it, whether it makes sense to use it in your application, how to start using it, and how to get access to CUDA hardware if you need to. So, what is Numba? It is a compiler for Python, and it's mainly aimed at array-oriented numerical code. So it's a tool that you would use when you want to get better performance out of your Python code. And it gets better performance by taking the Python code and compiling it into native code instead of having it execute in the Python interpreter. So there's actually a whole range of things that you could do when you've got Python code and you want it to run faster. Numba is just one of the options that you could look at. So for example, some of the other options that you might consider instead are to use a native library that does what you need, maybe adding some Python bindings for it if they don't exist already. You might compile your Python code with Python instead and maybe add some Python specific things to it. You might run your code under PyPy, which is another Python runtime, and that JIT compiles all of the Python language. Or you might look at using Julia instead, and I think there's some sessions on that tomorrow that I'm quite looking forward to. So Numba compiles Python, but it only compiles a subset of Python. It doesn't support all the language features in the entire library ecosystem. It mainly focuses on the subset that generally appears in numerical code, and we've put a lot of effort into covering as much of NumPy's API as possible. So because Numba doesn't support all of Python code, you have to tell it the functions that you want it to compile using the JIT decorator. So I've got a very short example in the notebook here. We'll ignore the imports and the parameters for now. The key point is that we have these functions, mandel and create fractal. These are Python functions all written in Python that were decorated with the JIT decorator here and here. And then we can call them that function as normal.
Graham,
so,
can you just make it a little bit bigger?
Yeah, I can. Well, I can try. Let me try.
Just one or two plus should be enough.
How does that look?
Great. That's great. Thanks.
Okay. So that was the create fractal and mandel code decorated with Numba's JIT decorators, just in case that was a bit hard to catch the first time around. Then beneath it, we've got some code to call the function, timing its execution. So if we call that, then hopefully in a moment, what do we see? A fractal and the execution time, which was about 0.4 seconds. So what actually happened during those 0.4 seconds? If to investigate that a bit, let's call the function again and see how long it takes this time. So for the second run, it seems to be much faster than the first time, around 0.06 seconds. And what we're seeing in this second run is how long the function is actually taking to execute. In that very first run, by the way, do you see my mouse pointer? Can I use that to indicate things?
Yeah, we can see the mouse.
Okay, cool. Yeah, so in this first run, we timed Numba, taking the Python function, compiling it into native code, as well as the execution. So after the first run, it's already got the native code ready to use. So the very first run always takes a bit longer than the subsequent runs. So how does this compare to the original Python code? We can call that with pyfunc. So if we do that, then what we see is that it takes a bit over half a second. So the Numba compiled function in this case was about 10 times faster than the Python. Typically, the speedups that you'd see with Numba over pure Python code can be from around 10 times up to the low hundreds, sometimes 100 or 200 times. This particular example is one that I picked because it's quite easy to demonstrate Numba with it rather than it being a showcase of the best performance that you can get out of Numba. So next, let's have a look at what happened when we called that function. And what Numba did. So we're going to do that by having a look at this diagram, if I can squeeze them both on, this diagram of Numba's compilation pipeline. And then this is a very sort of high-level diagram of Numba's architecture. So Numba actually compiles Python bytecode rather than Python source code because that's a lot easier to work with. So the first thing it does when you call a JITted function is it will use the Python bytecode compiler to get the bytecode, and then it will translate that into its own intermediate representation. It uses that intermediate representation to do something called type inference, where it will work out the type of every variable and value inside the function. And the reason it has to do that is because it eventually wants to generate native code. And that's always written in terms of specific data types and widths, so like an 8-bit integer or 64-bit floating point value. Whereas the Python source didn't have any typing in it. Python just uses duck typing, where any type of object will be accepted as long as it's got the right properties and methods. The next important stage after it's worked out all the types is the lowering stage, and that converts Numba's intermediate representation into the LLVM intermediate representation. So LLVM is a compiler framework that's used to implement lots of different compilers. Which is a really useful tool because you can use it to implement a compiler targeting lots of different machines, so x86 or ARM or CUDA. And all you have to do is target or generate LLVM's intermediate representation. So really the work of Numba is to take Python code and turn it into LLVM IR. Then we leave it to LLVM to do lots of clever optimizations on the IR and actually generate the machine code. So once it's done that, we're at this point where we have the machine code. It puts it in the cache in case we need it again later, and it can execute it. So that was a very high level overview of what Numba's doing when you call a JITted function. Next, who's using Numba? I don't know how big the Numba user community is, but I like to think of it as a reasonably successful open source project that's used by a fair number of libraries. I grabbed a few metrics from GitHub and Conda and PyPI that are in the notebook. I don't know how to make too deep an interpretation of these, but I think they show that it's of interest to more than just a handful of people. I did do a quick search to find a few applications of Numba from different fields of endeavor. One of them, Rapids, Ben talked about yesterday, that's a fairly heavy user of Numba, but there's some other links on the notebook and links to more links as well. In general, Numba tends to be a building block of an entire software stack, maybe rather than a tool that's directly used in the top layer of the stack. Maybe some of the libraries that you're using would make use of Numba. So why would you choose to use Numba in your own code or library? I think the main compelling argument for it is that you can keep all your code as Python code, and if you like, stay within your comfort zone, or perhaps the comfort zone of your collaborators, but still get better performance out of it. Some of the other options that I talked about earlier, like Python or using native code directly, mean you end up with code in a mix of languages or paradigms. Whereas if you use Numba and keep all your code in Python, then it can help you to focus your efforts on developing your algorithm and implementation, instead of maybe spending more time working in a language where you need to do a bit more management of things. And you can keep using all the same tools and frameworks, rather than maybe, for example, having a separate test framework for native code or something like that. So that's why you might choose to use it. Should you use it? Is it going to help speed up your particular code or application with a minimum of effort? There is a lot of nuance in the answer to that question, because there's lots of things that you can get Numba to do with some amount of effort. And we're always expanding its capabilities to try and support more language features and libraries and make it more extensible all the time. But the general answer is that if your code's fairly numerically oriented, and if you've got a lot of data and lots of iteration over that data, then it should be a reasonable fit for Numba. Things do get a little bit more complicated if you specifically decide that you want to use the parallel CPU target or the CUDA target, because you need to organize your code so that it can do lots of things in parallel. Some of the things that can be a bit more tricky to optimize with Numba, or things that I see as red flags when I'm deciding whether to use Numba, can be code that does lots of string processing or uses DICs heavily. So there is some support in Numba for strings and DICs, to some extent at least, but you can get a bit of a mixed bag of results with getting that code to compile or perhaps optimize well. Another thing is if your algorithms are inherently serial, then attempting to speed them up with a parallel device or parallel processing on the CPU or CUDA can be a bit problematic. But usually there's got to be some way to extract parallelism from something that's running long enough for you to think about accelerating it. It just might be that you need to rethink the way that your code's organized, or do a bit of refactoring of your code to get it that way. If your code already spends a lot of time inside native libraries that it's calling, or maybe you've rewritten portions of it with Python or a native language already, then it could be a bit of a slog to rewrite it back in Python to use with Numba. Finally, code that uses lots of object-oriented patterns and features doesn't necessarily translate well to using with Numba or perhaps CUDA. So I've mentioned CUDA a couple of times, and I haven't really explained what it is yet. So this is going to be a really quick overview of CUDA, just a very brief high-level one. The easiest way I find to think about it is first the hardware and then the software components. So the hardware is NVIDIA GPUs, and rather than going into depth about the architecture, there's basically two key points that I think you really need to understand when you're thinking about using them. The first is that GPUs tend to be a separate device from your CPU and main memory. They're connected to the system though, usually through a PCIe bus, and they've got their own onboard memory as well. So if you're going to use them, then you need to think about how you can efficiently get your data to and from them in the context of your program. The second point is that they're made up of a large number of cores that all execute in parallel on the same function. So you would literally have thousands of cores compared to the tens of cores that you might have in a big CPU. So that means you need to think about how to get each of those cores working on its own individual item of data. On the software side, because there's lots of cores, we've got to have lots of threads of execution. So typically those threads will be grouped into blocks of threads. And to a rough approximation, all the threads in a block are going to be doing the same thing at the same time on different items of data. Then you would have lots of blocks that make up the grid of blocks. Different blocks in the grid could be at different places in the function doing different things. You can have some communication between blocks as well, but you would tend not to have too much inter-block communication because that could start to become a bottleneck. So that was a little bit of an abstract presentation of the CUDA hardware and software. And we'll come back to that a little bit more in a more concrete way in the demonstration. So everybody's already got access to a CPU. There's one in your laptop, desktop, HPC node, whatever you're using. Not everybody's got an NVIDIA GPU in every machine. So if you want to start experimenting with CUDA, then there's a few different options that I'll talk about here. One Ben talked about yesterday is Google Colab. So I'm just going to quickly demo that now. You go to colab.research.google.com. So I think if I click that, hopefully that pops up. I'm just going to open this notebook that I'm using in Colab. So PyHEP 2021. With a bit of luck, I can open this. That one, I think. Now, if you want to use a GPU on Colab, you do need to go to Runtime, change runtime type, set your hardware accelerator to be GPU. And while we're here, I'm just going to pop down to the demo section of the notebook, start off a couple of things there for us to look at before we go back to the other presentation of it. So all I'm really going to do here in a bunch of imports is import Numba and see what the Numba version is and see what GPU it's given us.
Grant, is this something that we'd be able to do also while we're watching this talk?
Yes, I don't know what happens if loads and loads of people all try and do the exact same thing though, but you can certainly give it a try.
So the link here for Google Colab just goes to Google Colab in general.
Yes, that's correct. Yeah.
Then we have to type in the notebook link.
I think there was a GitHub tab. Let me go to that again, and then I'll just go through it a little more slowly. So if you click GitHub,
And what do we paste there? B.
and then it was gmarkle/PyHEP 2021.
Okay.
Uh,
This can resolve into a URL. I'd like to put the URL where everyone can see it, so you can do it in one click.
oh, okay. I mean, I could, yeah.
Okay.
It's a little difficult for me to do that because I'm not signed into anything on this machine. But are you okay?
Right. I've got it up,
Okay.
and there's a share button here.
Oh, okay.
Try copying this to Slido and see if that'll make it so that everybody can click it. Then we'll see if we bring it down. Okay. Thank you.
Okay. Are you happy for me to proceed at this point?
Oh yeah, please do. I'll try to share this.
Okay. Okay. So if you skip down to the demonstration section and the imports, then I'm going to have to go a bit fast for people to follow on, otherwise I won't keep to time. But you can sort of kind of catch up in a minute. Oh yeah, so the two things I'm interested in are the Numba version. On Colab you get 0.51, which is a little old now. There's we're a couple of releases on from that, but this is good enough for anything CUDA related really, certainly for getting started. Secondly, if you call CUDA.detect, it shows you what GPU you get. So Ben said yesterday you get a mix of different GPUs, or I don't know if you definitely get one or whether it's just more of a request. I've got lucky this time, I've got a Tesla T4, but you might sometimes get a K80 or a K40. So if you want to know what GPU you're using, use CUDA.detect. I also like to check what CPU I get with Colab as well. In particular, I do it in this notebook because there's also a demo part with the parallel target. So normally I get 2 Xeon cores. So yeah, import Numba, the Numba version, CUDA detect, and then check what the CPU is. I'm just going to go back to the rest of the presentation notebook for now. So I think we've kind of gone over most of the pros and cons there. Oh, it's free. That's a pro. You can get started playing with the GPU right away if you use Colab, and you can do it with Jupyter notebooks as well. On the downside, I guess you've got limited control over the instance that you're using. You don't get the latest version of Numba, but it's not a problem for getting started. Maybe you won't get the GPU you wanted. And if you don't like Jupyter notebooks, maybe that would be, maybe you'd see that as a con. I don't know. It's also a pro. If you've done a bit with Colab or you want to go straight to using a GPU in your own machine to move on from that, if you do have your own GPU, then your availability is consistent. You've always got access to your own GPU. You can install or run anything on your own machine, do whatever you like with the software stack, the latest version of Numba or whatever. And you can do things that would interrupt the GPU as well, like using the debugger if you want. On the downside, if you buy, although you can use any recent GPU, if you buy a low-end gaming GPU, you're going to get lower performance than, say, some pro-grade hardware like a T4 I just got on Colab. Especially if you, for 64-bit floating point, which tends to be a lot slower on the consumer devices. You'll also have to look after your own software stack. Not everybody wants that hassle. And at the moment, because of about a bunch of different conditions in the world, it's a little bit hard to get hold of high-end GPUs. So what I'd recommend if you want to get a card because Colab's not suitable, you kind of want to move on from it, is something like a 10 series GTX because they're old enough that you can get one at a reasonable cost. And most CUDA Numba features are going to work on it. If you get a GTX 1050, you just need a PCI slot. You don't need a giant power supply with loads of power connectors. And that's really a good enough system for doing most 95% of your development and debugging on. Once you've got everything working, you're happy with it, then you can start thinking about moving to higher performance systems later. If you're thinking about moving to a higher performance system, maybe you could use an HPC system you've already got access to. Some systems have GPUs or nodes or queues where you can get access to a GPU, along with the usual downsides that it can be hard to work interactively on some of them systems or all the usual batch job submission hassles. Alternatively, the major cloud providers offer instances with GPUs as well, which I think Ben mentioned as well. So that kind of concludes the overview of Numba and CUDA and getting access to a device. So what I'm going to do it. Oh, go on.
This might be a good time to look at the questions on Slido.
Oh, right. Okay.
You have the link to that?
Yeah, I had it open, but I. Oops. Sorry, I've.
Yeah, if you just drag
Okay.
the tab into the screen, into the window you're sharing, and make it big.
I see. So the first question is, how does Numba handle different machines where you may not know the hardware available? For instance, between a laptop, desktop, or specialized cluster. If you write, so one way of answering that is that if you write a CUDA kernel, it's going to, as long as the GPU you're using supports the feature that you're using, which is going to be almost always the case. There's very few features that are limited to specific GPUs available in Numba. It will just run on any GPU. The only thing you might need to be mindful of is that some GPUs have different GPUs have different limitations on the number of threads. So you need to write your program to be aware of that. There's APIs that you can use to query to what the limitations are. If there's time left at the end, I'll go into more detail about that. The next question is, to run this notebook locally with our own GPU, we just need the CUDA toolkit. Yes. Well, as long as you've got Numba installed, you can use the CUDA toolkit as well. If you're using Conda, then you can run Conda install CUDA toolkit, and you will get a CUDA toolkit. That's probably the easiest way to get it. Jim's, all right, that's just the link. Another question: have you got an indication of usage of Numba and HEP specifically? I don't. I have to admit that the HEP field is one that I'm really relatively ignorant of. The second part of the question, are you in touch with some people to get there by chance? Perhaps I'll try to clarify that at the end. If I don't move on, then I don't think I'll get through the demo. So I'm going to flip back to Colab for the rest of the demo. And it's a very simple diffusion code. In the initial condition, we start with like a Gaussian hump of tracer, and then a finite difference kernel diffuses it over many iterations. So there's a couple of different parameters in the notebook that you can play with if you like. 20,000 iterations, and the grid is 1,000 by 1,000, which is a reasonable enough workload to make use of a GPU. So we'll set them. The next cell generates the initial conditions. I don't think it's very interesting how the initial conditions are exactly generated or what they are. The only thing I'd mention is I use Numba's ngit decorator to speed up the generation of the initial conditions. So if we run that, we should get like a nice hump of tracer in the middle of the domain to start with. So first, for reference, there's the Python version, which is this smooth function. We've got a loop over the domain I and j indices, and then inside the body of the loop, we calculate the new value for this point as being some kind of average of the values of the old, previous iteration. When we run that, we run it in a loop, as many iterations as there are, and then every iteration we swap around the input and output arrays so that we don't accidentally overwrite our input. Now, I've actually got it commented out in the notebook for this demo because I think it might take too long to run. But if you want to run it, then you could uncomment this to run it. So we'll skip over that actual execution. Next, to demonstrate using Numba's parallel CPU target, there's a couple of changes that we would make to that code to do that. The first is to add the ngit decorator. Secondly, if you want Numba to parallelize, then you have to pass it parallel equals true as well. When you pass it that, it knows that you want to parallelize, but it doesn't necessarily know how. If you write NumPy array expressions, it can automatically parallelize those. But if you're using for loops, then you have to be a bit more explicit and tell it what you want to be parallel. So here I'm parallelizing the outer loop with prange, and then that tells Numba to parallelize the loop over the I index. inside the body of the loop, the computation is exactly the same as it was before. The only thing we do when we're calling it is that's different from the Python version is I'm going to make one call to the function before we start timing. And the reason for that is, as I mentioned before, the first call is going to include the compilation as well. So we just get the compilation out of the way before we start doing the timing. So if we run this, it might take a few seconds. On Colab, this issue pops up about TBB, but we're not using the TBB threading layer, and this probably won't happen on your own system anyway. It's just some old version of something. So we look, okay, we've got a slightly diffused tracer. So that was the CPU parallel implementation. Now a very quick look over a modification to that to use the CUDA target instead. So there's a few more changes that we need to make here. First is we'd use the CUDA.JIT decorator instead. Secondly, the for loop's gone. There's no for I or for j. Instead, what we'd do is this function would be invoked with as many threads as we had iterations of the loop. And each thread has its own I and j index. Now, each thread can use the CUDA.grid function to find out what its index is. And because we're using a 2D grid, pass 2, and then we'll get 2 indices back, I and j. It might be the case that we've got more threads than there are elements in the domain that we want to work with. So we have these checks to make sure that our particular thread is within the domain. This is just checking that we're inside an inner point in the domain. Then we use the if condition with those. If a thread happens to be outside the domain, then it'll just run this function to completion, doing nothing. If it's in the domain, then it does the exact same computation as before. There's a couple more changes when it comes to calling it. As I mentioned earlier, the GPU has a separate memory, so the best thing to do is to move the data over to the device before we start doing anything. Then we allocate some space for the next iteration as well on the GPU. We're warming up the JIT just like we did before, making one call to do the initial compile. But another thing we have to do, because we're launching with lots of threads, we need to tell how many threads we want to launch with, and that's done with this square braces syntax, what the size of the grid is and what the size of the blocks are. So I start with a slightly arbitrary choice of block size, 16 by 16, which is kind of reasonable, but kind of arbitrary for this problem. And then we need to make sure there's enough grids, blocks of that size in the grid to cover the entire domain. So we can compute the size of the grid as a function of the size of the domain and the size of the blocks. Then once we've made that call, our loop is the same as it was before, except with the kernel launch parameters as well. After the loop, we have this call to CUDA.synchronize that we need to have. And that's to make sure that the GPU is finished executing before we stop timing. So what happens when we make these calls to launch the CUDA function on the device is the CPU code can return immediately and carry on doing something. And this gets added to a queue of functions that are going to be called on the device. So you can end, if you don't have CUDA.synchronize, this loop can finish very, very fast as it tells the device to run all these kernels. And what you'd end up doing is just timing how long it takes to enqueue the kernels rather than how long it takes to run them. So if you have CUDA.synchronize, the CPU waits for the device to finish executing all its kernels before we record the end time. So if we run that, it should take a couple of seconds and hopefully we get a similar looking result to the CPU. Yep, hopefully. If we compare the results, the difference between the CPU result and the CUDA result should look pretty zero everywhere. Of course, it's always good to have a programmatic check of the correctness. So just an assert to make sure the CPU and CUDA times are close. If they are, let's see how long it took to execute. So in this case, the CUDA GPU is a few times faster than the CPU. Again, depending on what GPU you're using, what CPU you're using, what the problem, what your code is like, what optimization you've done, you can get really varied results. This isn't necessarily the fastest speed that we could get with the GPU, but it's one that's easy to demonstrate. You can get lots, very sort of varied, different levels of speed up, sometimes much better than what we're seeing here. So if this all seems interesting, you want to experiment with it and learn a bit more about it, there's some links to some resources for using Numba. There's a fairly comprehensive Numba and CUDA course on the Numba GitHub. If you want a quick intro, then there's a 5-minute guide in the documentation. There's a couple of links to learn more about how Numba works. The life of a Numba kernel post goes through a lot more detail of the pipeline, as does the documentation. If you specifically for CUDA, an even easier introduction to CUDA is a simple blog post. Then you can look at the programming guide for more in-depth coverage and reference. If you want to get help with Numba, there's the Gitter channel. Drop in, say hi. It's good for quick questions and interactive discussion for the quick things. The discourse forum's pretty active. There's lots of helpful users in there, and it's good if you've got to share more code, links to repositories, or have more in-depth questions. Then there's the issue tracker you can search if you're having some issues as well. Not usually your first port of call for making a question or request, but we try and keep it just for reporting bugs and feature requests. So that concludes the demo as well.